Hello everyone, welcome to SNR Tutorials. In today's session, we'll be learning about one of the most important network theorems, that is Thevenin's theorem. This topic belongs to Chapter 3, Network Theorems, and it is a very useful method for simplifying complex electrical circuits. By the end of this video, you will understand how to calculate Thevenin's equivalent voltage, equivalent resistance, and how to determine the load current using the simplified circuit. So, let's get started. So, the Thevenin's theorem states that any linear two-terminal network containing voltage sources, current sources, and resistors can be replaced by an equivalent circuit consisting of a single voltage source in series with a single resistance connected to the load. This equivalent voltage is called Thevenin's voltage, denoted by VTH, and the series resistance is called Thevenin's resistance, denoted by RTH. In simple words, instead of analyzing a big messy network, we can represent the entire circuit by just one voltage source and one resistor. On the left hand side of the screen, you can see the original complex circuit, and on the right hand side is its Thevenin's equivalent, a single voltage source VTH in series with RTH connected to the same load resistor RL. Isn't it that simple and elegant? Let's now look at the step-by-step procedure to find the Thevenin's equivalent circuit. Step 1. Remove the load resistor RL from the circuit. Find the open circuit voltage across the terminals where the load was connected. This open circuit voltage is called as VTH, the Thevenin's voltage. Step 2. Deactivate all the independent sources. This means we short circuit all the voltage sources and open circuit all the current sources. Now calculate the equivalent resistance between the same two terminals. The resistance is called RTH, the Thevenin's resistance. Step 3. Draw the Thevenin equivalent circuit. Replace the entire network by a single voltage source VTH in series with a single resistance RTH and connect the load resistor RL to this. So it is simplified. Using this reduced form, you can easily find the load current or power without having to solve large circuit equation each time. That's the power of Thevenin's theorem. Let's solve a simple example to understand how Thevenin's theorem works in practice. In this circuit, we have 10 volts voltage source connected to two resistors R1 that is equal to 2 ohms and R2 that is equal to 3 ohms connected in series. The load resistor RL is connected across 3 ohm resistor. Step 1. Finding VTH. First remove the load resistor and find the open circuit voltage across terminal A and B. Using the voltage divider rule, VTH equals 10 multiplied by 3 divided by 2 plus 3. That gives us VTH equals to 6 volts. Step 2. Find RTH. Next, deactivate the voltage source. Replace the 10 volt source with short circuit. Now the two resistors R1 and R2 are in parallel. So RTH equals 2 multiplied by 3 divided by 2 plus 3, which gives us 1.2 ohms. Step 3. Equivalent circuit. We can now draw the Thevenin's equivalent, a 6 volt source in series with 1.2 ohm resistor. Step 4. Finding load current. When we connect the load resistor of 3 ohms The current through it is given by I equals VTH divided by RTH plus RL. That is 6 divided by 1.2 plus 3, which is equal to 1.58 amperes. So the load current is 1.58 amps. As you can see, instead of solving the entire circuit each time, Thevenin's theorem helps us to replace it with a simple two-component equivalent circuit, making the analysis very fast and easy. So let's summarize what we learned today. Thevenin's theorem allows us to replace any linear network with a single voltage source VTH and single resistance RTH. It helps simplify circuit analysis, especially when the load keeps changing. We only need to recalculate the current using the same Thevenin's equivalent. I hope the session helped you understand the concept clearly. So in our next video, we'll discuss Norton's theorem, which is closely related to Thevenin's and uses the current source instead. Thanks for watching SNR tutorials. Don't forget to like, share and subscribe for more concept-wise explanation in network analysis.